Quick spin around the celestial sphere. Syracuse, Sicily, 212 BC. As far as topics of history go, astrology pretty much has it all: mystery, intrigue, romance, and every so often a rollicking, old-fashioned naval assault, like the one the Roman general Marcellus waged against the Sicilian fortress of Syracuse, whose citizens had sided with Rome's Archvo, the North African Empire of Carthage. But most of all, the history of astrology is filled with astronomy. Star, it's the starry thread that unites these stories and makes them sparkle. Being familiar, therefore, with even a little astronomy can help clear up a lot of astrology's blurriness. And this is what brings us to Syracuse, because all the astronomy we'll need in this book is hunkered behind those walls inside the workshop of the great Archimedes. The world in Rome's hands at the time of Rome's works against Carthage, the island of Sicily wasn't Italian but Greek. In fact, Cicero, the Roman orator, once described the Syracuse as the greatest and most beautiful of all the Greek cities, while Rome and Carthage dug it out for dominance of the Mediterranean. Sicily lay right in the middle, an urgent strategic prize. Thus, even though Rome had more immediate concerns, such as Hannibal and his elephants pillaging unchecked throughout Italy, an alliance between Carthage and Syracuse could not be permitted at any price. The Senate and the people of Rome therefore dispatched Marcus Claudius Marcellus with a fleet of ships and orders to bring Sicily to heel. Yet, the Roman armada of quintuple-decked warships soon discovered just how outclassed they were. Archimedes, the most brilliant engineer of the ancient world, had personally designed his city's defenses. The same genius who proved the law of the lever and who declared that he could lift the entire earth so long as he had another to stand on, had devised a terrifying machine which so it said, could hoist the Roman ships straight into the air and plunge them back into the sea. Thwarted by Archimedes' contraptions, Marcellus settled in for a siege. If this contest has been decided by engineering alone, no doubt that the Sicilian would still be speaking Greek today. But Marcellus was the master of a craft even more powerful than mechanics treachery. Through informants, he learned that Syracuse North Wall would be likely defended during the city's festival to Artemis, the virgin huntress and goddess of the moon. And so, unnoticed amid the nighttime revels, the Romans scaled the walls and snuck into the city. The ancient sources don't give a precise date of this, but we can offer what's probably a pretty good guess. First, the walls were breached sometime around the beginning of spring in 212 BC. This much we're told. Second, Artemis, being a lunar goddess, likely preferred her celebrations when the moon was full. Connecting these dots, it is possible that Syracuse's fate was set in the pre-dawn hours of April 1, 212 BC, during the Syracusan springtime lunar month of Artemisios, under a canopy of planets and stars resembling the scene depicted in Figure 30.1. Even as his troops plundered the city, Marcellus still hoped to meet the man whose creations had both baffled and amazed him. He was too late. One of his soldiers had slain the old engineer, still working it said on a problem of geometry. But we can imagine Marcellus wondered when he stepped into the great man's study. Amid scattered diagrams and half-built prototypes, two strange-looking objects attracted his gaze. They were two models of the cosmos in miniature. The first was a small, solid sphere whose surface was dotted with stars. The second was an entire clockwork universe complete with orbiting planets. Out of all the spoils, Michael shipped back. The clockwork planetarium was the only item he kept for himself. The starry sphere, meanwhile, he gave to the temple fleet in Rome. Surprisingly, the Roman descriptions of these two little universes provide some of the best information we have about the otherwise forgotten beginnings of Greek astronomy, and it is Hsieh who offers the full sketch. He writes that Thales circa 550 BC was the first to fabricate a spherical globe, while Ephemeris circa 350 BC, a student of Plato's, was the first to engrave one with a map of the stars. Aratus the poet, circa 250 BC, immortalized Ephesus spell in a much-loved poem called Phenomena, but it was Archimedes who was the first to bring one to live with mechanical motions for the sun, moon, and planets. Remarkably, a recently as the 20th century, 30 facts from around the time of Cicero turn up which may very well be copies or descendants of Archimedes' cosmic model split 5. The first is a silver sphere about the size of a tennis ball, adorned with the constellations. The second is the extraordinary. The second is the extraordinary antikythera mechanism, a multifunctional crank-operated astronomical calculator and the only clockwork gauge to have survived from classical antiquity. So what information did these cosmic contrivances include? This is the question we now turn to. Stylo and Stylo. From Archimedes' era right up through the Renaissance, the universe was thought to look more or less like figure 3.2, anchored at the center was the spherical earth. The Greeks were certainly aware that the earth was rod, which never moved, not even to spin around on its axis. Furthest away were the stars, which made a clockwise or east to west revolution around the earth once per day. Between the stars and the earth were the seven spherical planets is nested in their own spherical shell. Through a sort of celestial friction, the stars drag each of these shells or spheres along with them in the revolution around the earth. Thus the movement of the outermost starry sphere set in the motion the sphere of Saturn, albeit with a bit of lag. Saturn's motion in turn dragged Jupiter's sphere by the gate at the slightly slower rate. Jupiter then dragged Mars the Sun, so on down to the moon. Because each celestial sphere revolved a little bit slower than the one above it, David was that in addition to the daily east to west revolution, each planet appeared to slip backward or west to east at different speeds as measured against the background of the big stars. Saturn slipped the most slowly, such that it takes nearly 30 years for it to make a complete lap around the stars. Next is Jupiter, which orbits is approximately 12 years. The interval needed for the Sun to overlook the same stars twice the rise exactly 1 year. Lastly and swiftest is the Moon, which was completely backward around the stars once every month. The Babylonians, as far as is known, never had use for cosmic models like this. Speculating over the physical arrangement of the heavens appears to have been a peculiarly Greek pastime, one they enjoyed so much they had two different names for it, astrologia and astronomia. These two words, astrology, and astronomy. These two words emerged early on as synonyms, despite being formed from different etymological elements. Astronomia is a compound of aster meaning star or planet and nomos meaning law. Meanwhile, astrology, astronomy, and derives from logos, which means word or speech. Very literally, then astronomy is the star law, while astrology is star law. The word logos, however, is notoriously versatile and often carries the added nuance of system. Thus, a more meaningful translation of astrology might be a systematic account of the stars and planets. Yet, why have two different words to mean exactly the same thing? There's really no other ancient Greek word pair that's comparable. Today we have economy and ecology, both from ecos meaning house. But while the first word is genuinely ancient, the latter is thoroughly modern, and indeed these two words have little connection to each other. There may not be a good answer here. Nevertheless, we can make note of the fact that the earliest astronomy astrology split in Greek alliance with the planet chasm dividing all of ancient Greek thought. That between Plato and Aristotle. Plato in his writings, and most notably the Republic, relies solely on the word astronomia. Meanwhile, Plato's most famous student, Aristotle, exclusively used the word astrology in his books such as Physics, Metaphysics, and On the Heavens. It's tempting to interpret these competing word choices as a reflection of the competing philosophies. Did Plato envision astronomy as the law, as approaching his idea of pure, abstract, and mathematical science? Conversely, did Aristotle purposely use astrology as the law to counter that knowledge must be empirical and inductive? Unfortunately, there's not a whole lot to support this reading. Both Plato and Aristotle categorize astronomy astrology as a branch of mathematics, and neither indicates that he is using anything other than a common and commonly understood word. Besides, even if there is a deeper significance to this distinction, it doesn't do much to explain the subsequent histories of these words. For one thing, Aristotle influenced the development of the natural sciences in a way that Plato quite simply did not. It was Aristotle's vision of the cosmos and his terminology which constituted the scientific consensus when Archimedes constructed the celestial model. This doesn't mean, however, that there weren't alternative ideas orbiting around. In fact, it's through Archimedes that we learn about another thinker, a certain Aristarchus of Samos, who argued that the sun, not the earth, stood at the center of the universe. It's amazing to consider, but Copernicus' idea of a sun-centered cosmos was actually proposed thousands of years before the scientific revolution. It's more amazingly, the question of whether the Earth orbits the Sun or vice versa, the very question on which the whole scientific revolution is supposed to have hinged, may not have been viewed as particularly important, at least not to Archimedes. At the time, the abstract cosmological speculations of those whom Archimedes called astrologers astrology, that is, who, that is, those who studied astrology had not real bearing on the practical problems of computing when and where the various heavenly bodies would appear in the sky. For this existed an entirely separate and more mathematical tradition, one which intricate numerical methods provided the perfect matrix for astrology meant here in our modern sense of the word to establish its roots multiply, mapping the sky. Supposing Suppose you saw something dancing in the sky like a planet or a beautiful star. How would you point it out? If gesturing does the trick, great. But if not, you're left with see such and such off to the right. Okay, stop. Now look up just so high. All things considered, it's not an ineffective method. Not though that it would never occur to anyone to it and look for it at a distance of so many millions of miles away. because when we look up at the sky, everything beyond the clouds, the sun, the moon, the stars, the planets seems equally far away, as if it had all been painted on the inside surface of an enormous sphere. This sphere has a technical name, the celestial sphere. It's basically a giant fictitious globe centered around the globe of the Earth, which provides a reference for locating distant objects in the sky, and it's between these two globes, the celestial above and the terrestrial below, that astrology makes its home. Often it's objected that astrology must be wrong because it relies on geocentric, that is earth-centered, concepts like the celestial sphere, whereas it's been known since Copernicus that the Earth revolves around the Sun and not the other way around. Leaving astrology's fundamental soundness aside, there is nothing at all backward about adopting a geocentric framework. Geocentric coordinates are still used every day in the most advanced applications of satellite navigation, mapping, and even astronomy. If anything, the Copernican revolution emphasized the importance of finding the most appropriate coordinate system for a given problem. And when it comes to measuring the positions of heavenly bodies as they are seen from the Earth, geocentric coordinates are often the most convenient choice. Thus, despite millennia of scientific upheaval, the basic geocentric coordinates that we'll use throughout this book will be as familiar to astronomers today as they were to Archimedes thousands of years ago. In fact, a big reason why the celestial sphere was remained so useful for so long is precisely because it doesn't require any assumptions about the actual physical arrangement of the cosmos. It's simply a handy framework for modeling emotions in the sky, and we don't need to look very far either for an effective method to specify points on its surface. The system of latitudes and longitudes we're familiar with from geography is as effective in heaven as it is on earth. But there's one important wrinkle. Here on Earth, the Earth's daily rotation provides a natural rotation around which to construct a latitude-longitude coordinate system due to heaven's multiple motions. However, there is no single obvious orientation to choose. Actually, there are three. These three choices yield three separate geocentric coordinate systems, each tailored to treat a separate set of celestial phenomena with maximum ease. The system of equatorial coordinates is what would result if the Earth's latitudes and longitudes were extended out to the heavens. The system's fundamental mid-planet coincides with the Earth's equator, and its central axis coincides with the Earth's axis of rotation. Line of longitudes. Line of longitude are called right ascensions and measured in terms of hours, minutes, and seconds. Lines of latitude are called declinations. By design, equatorial coordinates are constructed to line up with the sky's apparent daily rotation, which makes these coordinates the simplest and most natural system with which to treat day's motion. The coordinates are constructed around the sun's yearly motion in the sky. And as a quick glance in figure 3.3 shows, the plane is a planet of this motion. The plane of the ecliptic doesn't line up with the equatorial coordinate system at all. Instead, the ecliptic is inclined to the equator at the angle of about 23.4 degrees. But if it weren't for this angle, there wouldn't be any seasons. This is because the sun's orbit along the ecliptic carries it further north of the equator at certain times of the year and further south at others, making the sun appear higher or lower in the sky depending on your latitude. Astronomy would undoubtedly be simpler, but much more bland, if the ecliptic were inclined to the equator as such a varying angle, but one advantage of waving fundamental cycles in the sky, the equator and the ecliptic instead of just one, is that the two locations where these cycles intersect offer two natural points of reference. These are the spring and fall equinoxes on the 2 days of the year when the sun crosses the equator at one of these points. The Earth experiences a perfectly even 12 hours of daylight and 12 hours of night. These days therefore divide astronomically the first day of spring and the first day of fall. By tradition, both of the equatorial and ecliptic coordinate systems take the spring equinox of vernal point as their prime longitude. Here on Earth, by contrast, our system of longitudes has no natural starting point. The Earth's zero longitude or prime meridian is the line that runs through the UK's Royal Observation at Greenwich, a cosmologically arbitrary compromise agreed upon by the nations of the world in 1884 at the International Meridian Conference in Washington, D.C. Latitude lines in the ecliptic coordinate system are called, not very creatively, ecliptic latitudes. Similarly, the longitude lines are called ecliptic longitudes, and they are measured as degrees from the spring equinox in the direction of the sun's annual motion. But recall that the stars along the ecliptic disk which the sun touches during its yearly orbit are the stars which form the zodiac constellations. By virtue of its location, therefore, the zodiac offers a complementary way of denoting ecliptic longitudes. Traditionally, this is done by fixing the first point of cusp of Aries at the vernal point. The other signs that then follow in 30-degree increments according to the system laid out in Figure 3.4. Thus, the fall equinox ecliptic longitude coincides with the cusp of Libra, while the cusp of Cancer ecliptic longitude and Capricorn ecliptic longitude 270 degree coincide with the solstice. One remnant of this tradition has persisted right down to modern times, in that the cycles stretched out by the sun on the summer and winter solstice are still called the tropics of Cancer and Capricorn. These celestial cycles projected back down to Earth define that warm and sunny region we call tropical, and whose boundaries correspond exactly to the obliquity of the ecliptic, namely the latitudes 23.4 north and 23.4 south degree of the equator. The word tropic, meanwhile, comes from the Greek word tropy, signifying a turn. It's related to the word trophy, which was a marker showing where the enemy's hand, where the enemy's army had been turned on the battlefield. By analogy, the trophy of Cancer and Capricorn mark the northernmost and southernmost excursions of the sun before it turns back to the equator. Before it turns back toward the equator. Ecliptic coordinates are designed to make it easy to track the sun's apparent yearly orbit, but they are handy for tracking the moon and the planets too. Due to the way the solar system first formed, the Earth, Moon, Sun, and planets are all situated very nearly on the same planet on the same plane in space. The ecliptic plane. This gives this gives the whole solar system like a disc-like structure, as no planet strays from the ecliptic by more than 9 degrees of ecliptic latitude. This behavior is often included on celestial globes in the breadth of the zodiac band drawn around the ecliptic. To give a specific example, the moon orbits the Earth on a plane that is offset from the ecliptic about 5.1 degrees. Were it not for this small offset, there would be a solar eclipse each and every month during the new moon when the moon and the sun align in ecliptic longitude. Clearly, this is not the case. The reason is that at most the moon is ever so slightly offset from the sun in ecliptic latitude. Since the sun is always, by definition, exactly on the ecliptic, it follows that no eclipse can occur unless, at the precise instant of new moon, the moon is also on the ecliptic and not smidgen above or below. You can see an example of this in the coordinates computed for the sun for the solar eclipse and amount in chapter 2. And this connection with eclipses is how the ecliptic got its name. Predicting eclipses is a tricky business in part because it requires an ability to accurately model the moon's ecliptic latitude as well as its ecliptic longitude. But in situations where that level of detail is needed, the disk-like structure of the solar system means that the position of the sun, moon, and planets can be communicated exactly effectively simply by reporting the ecliptic longitudes. This practice is especially characteristic of astrology, which simply adds a little pizzazz to the master of by using zodiac symbols to denote longitude increments of 30 degrees. For example, an ecliptic longitude of 127 degrees can be written as equivalently 7 since the zodiac sign of Leo 7 degrees. Since the zodiac sign of Leo begin ecliptic longitude of 120 degrees. During the course of a day, the ecliptic longitudes of the sun and planets remain more or less unchanged, but over longer time periods, each of these bodies makes its slow west to its orbit through the zodiac in the direction of increasing ecliptic longitude, that is, in the direction of Aries, Taurus, Gemini. Occasionally, however, each of the planets, but never the sun or moon, will appear to make a small loop-de-loop in the zodiac. When a planet wanders backward through the zodiac, that is, in the direction of decreasing ecliptic orbit or Aries Pisces Aquarius, it is said to be retrograde. Today, it's known that the behavior is simply the result of the Earth orbiting the Sun, but in the geocentric cosmos, modeling retrograde motion wasn't a simple matter at all. Nevertheless, it was this and other orbital anomalies which spurred the stargazers of antiquity to continually improve their models and predictions of the complex motions of the planets as seen from the Earth. The third and final system of standard geocentric coordinates are horizontal coordinates. These are based around you, the observer, wherever you happen to be. The fundamental midplane of the system is your local horizon. The system north pole is the spot in the sky directly over your head called your zenith. Latitude lines counting from horizon to zenith are called the elevations. Longitude lines are called azimuths, and they correspond to the direction which you will read of a map with local north or just often local south, serving as the zero longitude. However, horizontal coordinates are especially important from a practical standpoint, since these are the values you would read directly off an astronomical instrument. Converting to equatorial or ecliptic coordinates, it requires the geometric formula which traditionally might be approximated by handy algorithms, tablets in a book, or even the mechanical operations of a device like an slave. Level 3.1 summarizes the three geocentric coordinate systems just described. In the Sims of Heaven, I've included throughout this book the positions of each. The 7 classical planets are reported as latitude and longitude pairs in each of these three systems. That's a total of 6 coordinates per planet. The presence of a downward pointing arrow indicates that a planet is in retrograde. The seventh rightmost column in the same list, the astrological house of heaven in which each planet is located. This house is astrology's unique system of local coordinates. We'll discuss them in greater detail in chapter 8. In the meantime, simply by observing the themes which appear in each chapter and getting more comfortable with their coordinates, you feel increasingly at home inside the celestial sphere as you make your way through this book. Sun-based or star-based astrology, zodiac signs versus zodiac constellations. If you've been paying extra close attention, then perhaps you've noticed a very subtle but very important inconsistency in what's been discussed so far. In just 3 chapters, I've already mentioned two separate ways of dividing the zodiac. Chapter 1. When discussing the age of Aquarius, I described a method for dividing the ecliptic which ensures that as many stars as possible from a particular zodiac constellation ended up in the partition assigned to the zodiac sign. In this chapter, I've been referenced an entirely different system in which the spring equinox defines a cusp of Aries. As it turns out, these two methods are completely incompatible on account of the precision of the equinoxes. The vernal point will cycle through all 12 zodiac constellations over a period of approximately 36,000 years. And if the vernal point is taken as the cusp of Aries, then Aries, the sign, must slowly but inevitably slide away from the Aries, the constellation, and so too for Taurus, Gemini, Cancer, etc., such that in a few more centuries the zodiac sign of Aries will migrate all the way into the constellation of Aquarius. This situation is equally problematic for astronomy. The equatorial and ecliptic coordinate systems also use the spring equinox as the dominant origin, but because of the Earth's slow wobbling, which is the physical cause of precision, these systems of coordinates are in constant state of flux. This is a really unfortunate property for any coordinate system to have. Consequently, when specifying the astronomical coordinates of an object in the sky, it's also necessary to specify the epoch or instant in time to which those coordinates are referenced. Most modern astronomy uses the G20,000.0 epoch, which references the location of the spring equinox at noon in Greenwich on January 1st of the year 2000. More precisely, beginning in 1997, astronomers finally dispensed with using equinox reference points altogether and switched to the International Celestial Reference Frame, or ICRF. The ICRF is based on a set of extragalactic radio sources and is aligned for continuity and convenience to the G2000.0 epoch. In astrology, meanwhile, it's almost always preferable to give coordinates that are of date, that is, coordinates which are reference to the equinox of the specific moment in question. In our themes of heaven, ecliptic coordinates are always given of date, whereas equatorial coordinates are always given by respect to the ICRF G2000.0 reference frame. In practice, the precision of the equinoxes is so slow that, at least in astronomy, a given epoch can be handy for 50 or 100 years before it's worth the effort to retabulate all the star catalogs. But for astrology, precision is more than just a mere nuisance. It forces a fundamental choice as to whether you want a solar astrology in which the solstice and equinoxes are the main thing, or a sidereal that is star-based astrology in which the constellations are the main thing because you can have both. This inconsistency with precision makes a little bit worse each year. Would seem to have set the clock ticking for a pretty catastrophic crack-up of astrology's core beliefs, and yet no such crack-up ever occurred. Instead, Claudius Ptolemy, the most authoritative astronomer and astrologer of the ancient world, preemptively and definitively settled the matter in favor of solar astrology, and he did this remarkably early in astrology's history, around the year 150 of the Common Era, long before the slow divergence of solar areas from sidereal areas would have been seen as especially glaring or problematic. Ptolemy, who will meet again later in this book, never discusses this issue in detail. He simply adopts the practice of using the spring equinox to divine areas in both the Almagest, his book on astronomy, and the Tetrabiblos, his book on astrology, without offering much by way of explanation. But such was Ptolemy's prestige within the astrological tradition of Rome, Persia, Arabia, and Europe that there has never been a serious challenge to this convention. In other words, Western astrology is and generally always has been, and particularly solar. Occasionally, a few important stars may appear in horoscopes. Occasionally, a few important stars may appear in horoscopes here or there, but they are at most bit players. This is, to be sure, a third irony for a discipline called astrology, and whose most basic entities are named after constellations. Nevertheless, as early as Ptolemy's time, when the spring equinox was just beginning its precision to the constellation pieces, a decision was made. Whether controversially or not, we will never know, to dissociate the zodiac signs from their starry namesakes. And astrology has never looked back since. In zodiac sign, there is no denying that the zodiac signs called Aries, Taurus, Gemini, etc. share the same names as the constellations called Aries, Taurus, Gemini, etc., from which they arose. So it's not terribly surprising that news of the astrological divorce done finally some 2000 years ago has never really become common knowledge. This has set the stage for a classical comedy of errors, one that played most the one that played out most publicly in the recent discoveries repeated every 5 years or so of the existence of a 13th zodiac sign. A 13th zodiac sign, you may ask, what does that even mean? Think back 2 chapters to our somewhat quixotic computation for when the age of Aquarius will begin. Recall that the trickiest part wasn't projecting where the stars will be hundreds of years in the future, but rather how to draw the boundary between one constellation and the next, because traditionally the constellations never had precise boundaries or, for that matter, a consistent set of names, or even an ambiguous account of which stars belong where. Modern astronomy solves this problem, albeit in a somewhat arbitrary way. Today in astronomy, the constellations have no real function. At worst, they are an embarrassing reminder of an astrological past that most astronomers would just as soon forget. Nevertheless, when observing the heavens, it's useful to have a handy way to reference the large swathes of sky. The constellations serve this purpose just as well as would any other equally arbitrary ship. And so in 1922, the International Astronomical Union, IAU, which itself was only established in 1919, added at least recognizing 88 official constellations. These official constellations were given official boundaries in 1930, such that their complete set covers the entire celestial sphere with no overlap. The IO constellation boundaries are defined in terms of equatorial coordinates, that is, ascension and declinations. If you were to draw this is boundaries on the special celestial sphere, and there are called the sphere surface along its equator, you'd end up with a map which looks like figure 3.5. Note that in a map like this, the ecliptic cycle now appears as a sinusoid-like curve. The constellations intersected by this curve are shown in white. Sure enough, if you count them, they are 13. 12 are the familiar zodiac constellations, while the interloper here is Ophiuchus, the serpent bearer. Well, if we were hyperliteral types of regarding the IIU boundaries as possessing some sort of physical significance, as opposed to being an entirely arbitrary sim of convenience, then yes, we would be forced to conclude that there are 13 zodiacs. There are 13, not 12 zodiac signs. Cetus the sea monster and Orion the hunter both missed the cut by a whisker. We can even use this AU boundaries in construct I fully see the real 13 sign 13 sign zodiac stable 3.2 shows for the year 2020 simply by computing the dates when the sun will be present in each of these constellations. Exercises like this one have an amusing habit of throwing tabloid astrologers into a sort of essential dizzy. But while astrology is often loved for being helpless irrational, it must be admitted that in this instance, the traditional the astrological zodiac constructed around the equinoxes and solstices is indisputably more rational than the presumptively more astronomical zodiac constructed around the IIU constellation boundaries, which is totally arbitrary and more than a little absurd.